Okay, thank you. I thank the organizers for giving me an opportunity to present my work. So this is the title of my talk here, and these are the two references. If you want more details about my work, you can always look at these references. So I would like to thank the funding agencies, SERB and University of Hyderabad IOE Directorate for supporting me. This is my research group at University of Hyderabad. Sachidanand Das recently completed his PhD and he has joined IIT Kanpur as a postdoc. Vijay Kumar Sahu and Megha Bera, they are PhD students who are participating in this conference. Please look at their posters. I am not presenting their work here. And then Naveen is another young PhD student. Okay, and this is going to be the outline of my talk. There are 3 parts to my talk. And depending on the time, I'll cover whatever I can. Okay, so the first part, transverse response from anisotropic Fermi surfaces. So the simplest description of electrons in metal is basically p square by 2m Hamiltonian. So the dispersion basically looks like this, h cut square k square divided by 2m minus mu. Now m here is the effective mass and it changes from the metal to metal. Okay, so but there are some materials like for example ReSe2 where the effective mass m, it is direction dependent. Like for example the dispersion would be h cut square kx squared by 2mx plus h cut square ky square divided by 2my. So the Fermi surface that results from this kind of anisotropic kind of effective mass is basically elliptical Fermi surface. Okay, but let's say you take a 2-dimensional electron gas which is initially which has a circular Fermi surface. You can actually put a series of barriers in a particular direction to make the effective masses different in different directions. Okay, so that you can always do. Now, the claim of this work is that you take a Fermi surface which is anisotropic, like an elliptical Fermi surface, and you rotate the sample, like you rotate the sample by an angle phi, and you apply a bias along x direction. Okay, so now the major or minor axis of the Fermi surface is no more in the same direction as the bias direction. Now the claim is that you will get a transverse response. Okay, so that's the claim, and the reason why this happens is that let's say the major axis of this elliptical Fermi surface is along x-axis. Then for every kx ky, there is a kx comma minus ky, and the contributions from these two to the transverse current, they cancel. But when you rotate the Fermi surface, there is no kx ky and kx minus ky kind of pairs, so there is no cancellation. That's the reason for getting transverse response. Okay, so to solve this problem, what I did was I took this Hamiltonian for this. So this is the Hamiltonian. Basically, this is the kx square, this is the ky square. This is kx square, this is ky square, and this is a cross term also because I am rotating. Here, this delta, that's the anisotropy parameter, and this phi, that's the orientation of the Fermi ellipse. So you can rotate this thing I told, right? So this phi is the angle by which I am rotating. So you can see that when delta equal to 0, it is basically isotropic like free electron dispersion. And you can do Landauer-Buttiker formalism calculation where I actually calculate the change in the transverse current. I change in the transverse current the differential ratio of Iy to V. V is the potential difference I am applying along x direction, and Iy is the current that is flowing in the y direction. That is what I am interested in, and this can be kind of calculated in an analytical by an analytical expression, and the answer is basically this. And Gyx, so you see that in the limit of delta going to 0, this will be 0. That's because there is sign of eta minus eta prime. So you see eta and eta prime are given by these expressions. And also when phi equal to 0 or pi by 2, you will get this transverse response to be 0. And the plots, they look like this basically. So Gyx versus phi I am plotting. Okay, and these different curves are for different values of the bias. And what I was not sure was that, okay, this is basically I am taking a system which is infinite along y direction and using periodic boundary condition along y direction. But a realistic metal, a realistic sample if you take, it is, you cannot apply periodic boundary condition firstly. Other thing is it's not infinite. So now when you apply a current along x direction, will you measure a voltage along y direction? That was the question. And this question can be answered by this Buttiker probe method calculation. The important point here is basically to write down the Hamiltonian, which kind of captures this anisotropic Fermi surface. And one can write down the Hamiltonian in tight binding model. And that is basically this. You have a square lattice, but for this anisotropic Fermi surface, so you have diagonal hoppings also, which are unequal for the two diagonals. So if you choose the parameters appropriately, you can map on that continuum Hamiltonian to this lattice Hamiltonian. And then these are Buttiker probes essentially. So when you apply a bias from left to right, a current flows in the channel, transport channel, and a small current flows into the Buttiker probe also. And now what you do is you adjust the voltages of the Buttiker probe. You change it from 0 to, let's say, Vt. When you change it to Vt, some current flows from the Buttiker probe into the channel. Okay, so you choose this voltages Vt and Vb in the Buttiker probe in such a way that the net current that goes into the Buttiker probe, that is 0. Okay, so this has to be done numerically, and what we find is that this same kind of behavior is reproduced when you do the lattice model calculations. Okay, so basically here what I am kind of telling is that so this is the summary of this part. Basically what I am telling is that without the need of any magnetic field or even Berry curvature, some aspects of Hall physics one can get by very simple-minded in very simple-minded system. Okay, so this is the first part of my talk. So the next part of my talk is about altamagnets. I'll briefly introduce what altamagnets are and then present the results. So altamagnets are basically systems with net spin polarization that is 0, but they have again spin split band structure just like ferromagnets. So they have properties of both antiferromagnets and ferromagnets. Okay, so this is the Fermi surface for the ferromagnet. So there's a circle, the Fermi surface for a downspin which is smaller than the Fermi surface for the upspin. So there are more number of electrons, more number of upspin electrons compared to the downspin electrons in ferromagnet. And the important point to note here is that they are not degenerate. But if you draw the Fermi surfaces for the two spins in an antiferromagnetic metal, they fall on top of each other. Okay, so now in altamagnets again, so there is spin splitting. By that I mean they are not degenerate, and the net spin polarization is 0 because you see the size of the Fermi surface for the upspin and downspin, they are exactly same. Just that you take the downspin Fermi surface, rotate by 90 degrees, you will get the upspin Fermi surface. Okay, so the claim in this work is basically, okay, so then the interesting thing is basically that the spin split Fermi surface, it allows you to do a lot of spintronics applications and spintronics phenomena you can study. And one of the things is that you can take a junction between an altamagnet and a normal metal, and both have net spin polarization 0, but when you apply a bias from one to the other, you will get a net spin current. So that is something very interesting. And so they are basically promising platforms for spintronics applications without a need to apply magnetic fields. Okay. So now in this work, what I claim is basically that if you take a rectangular strip, a small rectangular strip of this altamagnet, that will have a net spin polarization, which is non-zero. Okay. So the reason for that is that, let's say you take a rectangular strip for altamagnet. So this is the kind of, so now actually there is this interesting kind of papers that are coming up in this thing in altamagnets. One can do basically Floquet thing with altamagnets. Fine, that's not what I'm doing actually. So you take a rectangular strip of this altamagnet and so it's basically the problem boils down to a particle in a box problem in a 2-dimension with a rectangular geometry. Okay, so when you have that, this is the kind of dispersion for altamagnet. So this is T into kx square plus ky square minus Tj into kx square minus ky square into S sigma, which takes plus or minus 1. So basically because of the rectangular geometry and because you have an anisotropic Fermi surface for upspin and downspin, which are elongated in different directions, you get a net spin polarization if you take a rectangular strip, and this happens. And this is true only in the small system size limit. If you take a very large system, that net spin polarization that goes to 0. So this is the spin, okay. So basically this is the physics behind that. So this delta k, the spacing between the k level spacing between the two discrete levels is basically pi by Lx and pi by Ly in the two directions. So because Lx is not equal to Ly, the spacings are different, and you have anisotropic Fermi surfaces, and that is what leads to this net spin polarization when Lx is not equal to Ly. Okay, so this color picture basically shows the normalized spin polarization, which is number of up spins minus number of down spins divided by the total number of electrons. So what I am doing here is I am taking a rectangular strip of this alto magnet, I am fixing a Fermi energy, and I am filling all the states that are below the Fermi energy, and all the states above the Fermi energy, they are empty. Okay, so I can count the number of up spins and number of down spins in this way. And this bright yellow patch, that basically tells that that it's fully upspin and no downspin, and this dark blue patch says that it's fully downspin but not upspin. So, but along the diagonal of this thing, which is basically Lx equal to Ly, you will get zero net spin polarization. Okay, so how do you, okay, this is fine, there's net spin polarization in a rectangular strip of alto magnet, but then the question is, how can you measure it if it's there? And the answer is that this is the proposal that I have. So you take a thin slab of alto magnet and you attach two pillars, one pillar on top, normal metal pillar, another pillar on the bottom, and now you apply a bias from top to bottom. Now this is normal metal, but still you will get a spin current, net spin current. That is because the alto magnet has a net spin polarization. And the next thing is you make the normal metal into a ferromagnet, and then you calculate the magnetoresistance. That is the, okay, and as a function of the magnetization of the ferromagnet. And what you see is that, so this is the picture, this is the plot of magnetoresistance versus the magnetization. So these are for different choice of Lx, Ly. So when it is rectangular, like, no, when it is square actually, the sample is like, the shape is like 10 by 10, then this magnetoresistance versus magnetization, so that's actually very much symmetric. Okay, when it is not, no more square, so the area is same actually for all these curves, area of the sample is same, but I am making it more and more rectangular, like Lx and Ly I am varying, so that Lx is not equal to Ly, but the Lx, Ly, the product is same. So it becomes like the slope of this thing, this curve Mr versus B at B equal to 0, that there's a non-zero slope that develops. Okay. Now if you plot the same thing versus B for larger and larger system sizes. So here in the right side plot, what I'm doing is I'm plotting magnetoresistance versus B for different system sizes. I'm fixing the aspect ratio. Lx to Ly ratio is same, but the I'm multiplying some constant to that Lx, Ly, and that constant is basically 2, 4 and things like that. So different curves are for different these things, and as the system size grows, that slope of this magnetoresistance versus the magnetization, so that goes to 0 here. So you can see, and now here that slope is what I'm plotting here versus the system size, it oscillates, and the large system size it goes to 0. Okay, so this is the summary of this work. Yeah, so that's the summary for this work, and this reference for this paper is Physical Review Materials, and it appeared in a special collection on alto magnets. The next part of my talk is about these topologically protected zero reflection points in junctions of multiple quantum wires, and this work I have done with Udit Khanna, who is also participating in this conference, and Professor Deepti Sen, who was my PhD advisor. Okay, so the reference for this paper is here. Please take a look at it and write to us if you have any suggestions or comments. Okay, so to tell you the story, so let's say you take a junction of n different quantum wires meeting at a single point. Okay, then what you can show is that, so you send an electron in one of the quantum wires and see how much is reflected, how much is transmitted. Okay, so then reflection probability, it is bounded from below by R minimum, and it's a function of n. Okay, and this R minimum, it is given by 1 minus 2 divided by n in fully symmetric junctions. So as n increases, you see that this R minimum, it approaches 1, which means that for large n, almost everything that you send will get completely reflected. The question we asked is, can you make something to the junction to get this reflection amplitude 0 for some set of parameters? And the answer is yes. And the proposal is the following. So instead of making this junction, all the quantum wires meet at a single point, you make a ring-like structure in the junction and tune the junction hopping parameter T prime. So for n equal to 5, I have the schematic here. So this is the kind of junction I have. So there is a polygon in the center. So these are the lattice points which have an on-site energy epsilon naught, and the hopping between the sides of the central polygon, that is T prime, and the hopping in the quantum wires, that is T. And now if I look for zero reflection points in the space of energy T prime and epsilon naught, think of these as three different parameters, I get zero reflection points like this. So you see this is the zero reflection point in the 3D space of energy epsilon naught and T prime. And this was the kind of initial finding, and what is interesting in this? Okay, zero reflection point is there, so what more? So the interesting point is that these are topologically protected. So what is the topology? How does it enter here? So the topology enters here because this reflection amplitude, it is a complex number. It is r e power, it's mod r e power I5. So now if you go around the zero reflection point, so let's say this is a zero reflection point in some T prime energy space, you go around the zero reflection point and you see how much the phase winds. It winds by 2 pi. Okay, because it winds by 2 pi, that's the topological protection for the zero reflection points. Okay, so around in this any point here, any zero reflection point, you take this loop, it has a winding number of plus or minus 1, which guarantees that there is a zero reflection point within that loop. Okay, so that's the topological protection, and here we have plotted the energy. It's on the left axis, and that's the T prime on the right axis for epsilon not equal to 0 as a function of n. And you see that this kind of, as n increases, this kind of reaches a common value, and we have analytical expressions with analytical proof for all these findings. So it basically approaches root 3 by 2. T prime goes to root 3 by 2 times T, and energy goes to 0. Okay, so this is a tight binding model. Okay, so zero energy means like it is in the middle of the band. Okay, so that is all fine. Now because it's topologically protected, now if you put disorder, that is, so the red point here in this energy T prime space, that is the zero reflection point for the clean case. Now you put disorder on the sides of the polygon, the central polygon. Then the zero reflection points, they don't disappear. For weak disorder, they get just displaced in the ET prime space. So these are for the 5-wire junction, these are the 5 different zero reflection points. Okay, so that is the thing. And something very, very interesting which we found towards the end of this project is that you take 4-wire junction and put a pi flux. Pi flux, it does not break time reversal symmetry, right? So what do you get in pi flux? So then when you have pi flux and let's say epsilon not equal to 0, then let's say T prime, you make it as T divided by root 2. What you get is that you get perfect transmission at all energies. That is zero reflection at all incident energies you get. Okay, and that is also topologically protected. Okay, so these are some important findings that I am telling you people, but there are more details about each part of my work, and please take a look at the paper if you are interested, and we can always discuss, and I'll be happy to take questions. And yeah, thank you for your attention. So I wanted to show the summary slide. Okay, that's the summary for the third part of my talk.
Sorry for many interruptions, and thank you for your patience.
Okay.
So the session is open for questions.
Hi, William, thanks.
Yeah.
So, what is the underlying symmetry that helps the protect topology here?
So in the first case, so when I said this junction, there is this thing called dihedral symmetry, which basically is that you take 1 to 2, 2 to 3, the cyclic kind of symmetry that is there. That is one thing. Then the other thing is there is this reflection symmetry, but they don't guarantee anything. So
reflection symmetry.
It is just the symmetry that is there in the system, but it doesn't guarantee the zero reflection. Zero reflection is kind of topologically protected. That's the understanding that we have at the moment of this thing.
Thanks.
Yeah.
Sir, in the spin polarization part, you said you need a junction of normal metal Altermagnet and normal metal. So
No. I just said normal metal altermagnet junction. That's all. And what I said in that is basically you take a junction of altermagnet and normal metal. Both have net spin polarization 0. But when you apply a bias at this junction, there's a spin current that flows. Yeah, that's all I said.
No, so my question is why this normal metal is required here?
It's not required. You take just an altermagnet and you apply current in a particular direction. It will carry a spin current. Yeah. Yeah.
Okay, thank you.
Yeah.
Sir.
Any other question? Yeah.
Thank you for a nice talk. So, in the last part of your presentation, you talk about this pi flux.
Yes.
So, pi flux, is it for that pentagon thing or?
No, it is for 4-wire junction. It's a square essentially, and all the sites in the central square, they are connected to leads. Okay, it's unlike your paper where you are connecting leads only to 2 sites. So here all the 4 sites are connected to the leads, and you put a pi flux. Yeah.
So, pi flux is basically localizing the electron, or it's just like you are saying that there is zero reflection?
Zero reflection. Yeah, it's not localizing the electron. Yeah, it's not localizing the electron because there are 4 wires. So I'll tell you. So you send electron in the wire 1, it will get transmitted into wire 2 and wire 4 equally. Probability of transmission is half to wire 2 and wire 4, and to the wire 3 it is 0. And the reflection back to the wire 1 also it's 0.
And is it for all the energies? Or?
All the energies. That is what is something very interesting that we find.
Okay.
Yeah.
Thanks.
Any other question?
Hi. So
Yes.
this is regarding the winding number.
Yeah, please. Yeah.
So you are defining the winding number from the reflection coefficient. How you are defining the winding number? Can you please repeat?
Yeah, so it's basically, there is this thing called the Cauchy argument principle in complex analysis. So any complex function which is a function of 2 parameters, let us say, you take a loop, okay, and you look at the phase, how the phase changes of the complex function.
Yeah.
And if it changes by 2 pi along a loop, this Cauchy argument principle guarantees that there is a 0 of that function within that loop.
Zero the poles like this.
I would not call it pole, I will call it 0. Pole is basically 1 over 0, right?
No, I mean the argument principle says
Argument
that
principle has that pole thing also, but I am taking the special case where the function function is bounded between 0 and 1.
Okay.
Okay, then it's 0 basically. So it guarantees that there is a one point where the function goes to exactly 0. That's the Cauchy argument principle.
Okay.
And from that I am defining the winding number, which is how it's basically how many times it winds by 2 pi.
Okay, I understood. Yeah. Thanks.
Yeah.
Okay. Let's thank Abhinav again for the nice talk.
Thanks.